Hello, this is a quick video on why we need to use the Verlet algorithm for time stepping for launching things into space. So first of all, let me do a quick repeat run so you can see this. Remember in class, we were launching objects up into space. The blue arc is the surface of the Earth. If I launch it at a higher speed, it'll go higher, so the Earth looks smaller. But let me reset that so that it looks like it did before. And we have a velocity time graph over to the right. Okay, so we start with a high positive velocity. We stop around 2,000 seconds. And we, plot until we hit the Earth's surface around just past 4,000 seconds. Okay, so notice we have thousands of seconds of time. All right, so as we go through this code, I've changed something here so that we can analyze how well Verlet works, okay? I've given a sum choice, which can be the old method that we had, which was Euler's method, using trapezoidal sums where we can, and choice 2 is using Verlet, all right? So let me first of all clear the command window, all right? And I'm going to start with the old method. I actually, with some choice, I came down here in the calculations section. If it's case 1, that would be using the old method. So I just took the code and I used, a simple trapezoidal sum, which you can see here in this line. Here's the trapezoidal sum. All right. And there is no V mid like there is in the Verlet algorithm. So remember, with the Verlet algorithm, we sort of step halfway and then finish the job with the second half step. So we do 2 half steps for velocity. There's a half step. Here's another half step. And we do that by creating a middle velocity that allows us to step. So you can see the Verlet algorithm is a little bit longer. So instead of 1, 2, 3, 4, 5, 6 lines of code, we have 1, 2, 3, 4, 5, 6, 7. We have 1 extra line of code in order to do the Verlet algorithm. So a little bit extra computation, but not much. But we're going to compare the results. Okay, so first I'll start with the improved Euler method. All right, given that we're plotting thousands of seconds of time, whoops, I don't want to change the mass, I want to change dt. Okay, so given that we're doing 4,000 seconds of time, I'm going to start with a dt value of about 10. All right, and I'll do the improved Euler method and I'll run. Okay, and the results are right here in the command window, which I just highlighted. Type 1 means we're doing the Euler method, okay? And notice it calculated the peak to be at about 6.62 million meters, okay? So that's just over 6,000 kilometers, approaching 7,000 kilometers in the air. All right. Now that's with a dt of 10, which you may think is kind of large, but out of 4,000, that's not so large. Now we know with sums that they get better. Whoops, I keep trying to change the mass as the time steps get smaller. So if I change dt down to 1, it will require me to do 10 times as many looping calculations. But we can see the result change significantly. Okay, so if we were trying to predict something for NASA, there's a big difference between 6.62 million and 6.704 million. Okay, so by lessening the time step, where our answer has to be better by making a smaller time step. So clearly, big steps are underestimating, because as we shrink the time step, the number's getting bigger, and it grew significantly. Let me make dt 0.1, and let's get a new result. Okay, so it goes up and down. All right, so it changed, but not by the same amount as before. Okay, so the amount of change from 6.704 to 6.712, okay, isn't that great. But remember, we're down to 1/10 of a second calculations out of thousands of seconds, okay, about roughly 4,000. So that's 40,000 calculation loops. All right. Now, to see how good this is, we need to just shrink dt even smaller. And when the changes become minimal, that's when we know we're calculating precisely enough. Okay, so we can see, oh, it actually came down a little bit. Okay, not sure why. Oh, I think we ran out of calculating space. Okay, this only allows me to do 10,000 calculations. So I think we didn't quite make it back to Earth. So anyway, let's hold with this number right here. The peak is around 6.7 million meters up. Okay, and by going to 1/10 of a second, we got there. Oh, we can see in the picture that we didn't really start coming back down all that much. So we may not have even reached the peak. So I'd have to change the code to allow for more calculations. We've exceeded the number of calculations that we're allowed to have because I put a stop in the while loop. Okay, when we try to do hundreds of seconds, it just doesn't go that far. So really the last good number is this number here. All right, 6.712 million. All right, now let's go over to the other algorithm. So we're going to switch over to Verlet. And let me go back to time steps of 10. Okay, so big time steps. So we did Verlet. Okay, that's why it says type 2 here in the command window with time steps of 10 seconds. And look at that, our peak is at about 6.712. Right? That agrees with the lowest for 1/10 of a second value for the peak using the Euler method. Okay, now let's go down to 1 second time step and run this again. And notice it did go a little bit higher. Okay, so the first number must have been an underestimate, but not by much. Okay, we're out to the 4th significant figure already. Okay, if we take dt and make it 0.1 and run this again, there's no change out to 4 significant figures. There would be a change if we went further, but not to 4 significant figures. So we can see Verlet with a 10-second time step gave us an answer that was only off by 1 in the 4th digit. So if we went out to 4 significant digits, the last digit is off by 1 with a 10-second time step. So rather than calculate down to the 1/10 of a second, we could use 10-second time steps if we're using Verlet, right? On the other hand, if we were using the Euler method, we really need to get down to a 1/10 of a second time step in order to get the same kind of precision that we had from Verlet. So we could say Verlet is about 100 times better. Okay, notice dt has to get down to 0.1 for the Euler method. That's with trapezoids, not a left or a right. Whereas at a 10-second time step, Verlet resulted in the same answer out to 4 significant figures. So we have, it takes 1/100th of the computational loops, okay, in order to use Verlet. So it's much more efficient, which is why it's used in things like video games where there's huge numbers of computations going on in order to make very complicated graphics move around. So the Verlet algorithm is much better. It took 1 extra line of code, but we could loop 1% as many times to get the same precision of answer. So that's why we'll be using Verlet in the future for many more analyzing motion that's a little bit more complicated.